Hi everyone, how are you doing? Today is the final week of our lecture classes, and I would like to turn your focus from linear algebra to multilinear algebra. So in the category of linear algebra, we consider linear functionals and linear transformations on a vector space. But now, instead, we consider bilinear guys. So why do we have to consider bilinear guys instead of just linear guys? Let me give you some motivation here. So we consider a vector space V, and there is a family of linear functionals on V, say Fi, indexed by some set. The set is called W. This is just a family in the dual space of V, which is linear functionals on V. And naturally, this now has a vector space structure. And we also require that the family of linear functionals depends linearly with respect to its index, which means that, okay, and linearly on I less than W, means that W as an index set, it also has a vector space structure, and this just implies that there is a linear map from W to V star, by mapping I to the linear function Fi. Right? Does that make sense? Yeah. Now we rewrite this linear map in another form. Say, why should we consider a linear map instead of a function with values in a fixed field? So we take B times W to F. Say we match each pair, say alpha, beta to F alpha and then beta. So this is a basic model that we turn the linear map from a space to another dual space to just a simple bilinear functions on the product of these two vector spaces. Okay, this is a basic observation, and it also our original source of motivations of our, in our style. Okay, bilinear. So you have just seen that bilinear guys just appears naturally in our field. Okay. So one important thing, maybe the most important thing about bilinear things, is the following degeneracy or indegeneracy. Okay. Degeneracy of a bilinear form, I will always write a bilinear form in Phi. Okay. Say on V. Say bilinear. Okay. So Phi is called non-degeneracy. Phi is called left non-degenerate if the following map, say, from V to W star, by sending this map alpha to Phi alpha with back to the second coordinate. So this is a linear function on W. Is an injective map. So it simply means that if Phi alpha beta vanishes for all beta in W, then alpha must be 0. Okay. Similarly, we could also define the right non-degeneracy, right? Called right non-degenerate if W to V star is mapped by sending beta to phi with respect to the first coordinate and beta is injected. Okay. And this is the basic property that we will consider about the bilinear form. Okay. So in some cases, this left non-degeneracy just coincide with the right degeneracy. For example, if this say let us be simple to make our life easier. Say V equals W and phi is symmetric, which means that phi alpha beta equals phi beta alpha. Then the left non-degeneracy is just equal to the right non-degeneracy. Okay, and of course, if when phi is alternating, means that phi alpha is 0 for n. Then, in particular, such a phi must be antisymmetric. But antisymmetric doesn't change the left or right non-degeneracy. So the same thing holds. And in this case, we will say that the perpendicular relation defined by phi is symmetric. Perp is symmetric. Yes. So you may imagine that if there is a vector v, there is a vector alpha in V, which is left perpendicular to a subspace U inside V, then it is also right perpendicular to that space. So geometrically speaking, this is very natural, and I will call this phenomenon symmetric perpendicular. Okay. Now we will mostly focus on this symmetric perpendicular case. Okay. So we start from general lemma as follows. Okay. The phi. Okay. Now phi is just a bilinear function on v times v. Bilinear. And with a symmetric perpendicular property, say for any alpha beta in V, phi alpha beta is 0 if and only if phi beta alpha is 0. Okay. Then we don't need to worry about the left perp or right perp of a given subspace. So for any given subspace W, we just define W perp to be those alpha in V, that you have phi alpha is vanishes on W. Okay, so of course by the assumption also equals to those alpha in V, and you got phi alpha vanishing. Okay. Then for subspace W, we have the restriction of this bilinear form, say phi, to W is non-degenerate. Okay. If and only if the intersection of W with its perp is trivial. Okay. Moreover, when this non-degeneracy restricted to a subspace holds, we will have a direct sum decomposition of our whole space. Say V equals W direct sum with W perp. Okay. So this is just a general lemma describing the decomposition property determined by a special bilinear form. Okay. And if you are familiar with the non-degeneracy here, this equivalence is clear, right? So a linear form when restricted to a subspace is non-degenerate just means that any vector in W which is perpendicular to W must be zero. Which means that, okay, if we have a vector in W which is also in W perp, then it must be zero. So this equivalence just follows from the definition. Now we only need to show this decomposition of our vector space V. So how do we do that? Yeah, since when this holds, we already have the trivial intersection of these two subspaces. So to show the direct sum decomposition, our knowledge, it's sufficient to show that these two subspaces have a sum of dimensions which is equal to V. Okay, to show, in other words, the dimension of W perp lies in the equals to the codimension of W, okay, which is just the dimension of V minus dimension of W. Okay. Now let's focus on this W perp. What is W perp? Okay, let me rewrite this definition here. W perp is just the common kernel subspace of this linear function on W. Which means that, okay, if so for example, if we take any beta from W and consider the linear functional determined by phi, blanket, and beta. Okay. Then, if alpha lies in the kernel of such linear functional, it just means that alpha is perpendicular to beta. And if this equation holds for all beta in W, then it means that alpha is perpendicular to all elements in W. So that's clear, right? Yeah. So it means that W perp just equals to the common kernel space of a family of linear functionals. Okay. So let's rewrite our original notation here. Say it is those beta, beta in W. Okay, this is a subspace of V star, the dual of V. Right? Then we take the common zero space which lies in V. So we have the dimension relation that the dimension of W perp just equals the codimension of such space in V star. Okay, that equals dimension of phi blanket data beta in W. But note that since phi is non-degenerate on W, we have this map from W to W star, sending beta to W through phi blanket beta is injective. So this subspace in this actually now in W star is just the image of such an injective map. So its dimension just equals to that of W. Okay, so this finished our proof. So this one is clear, if you are familiar with the definition of non-degeneracy. Okay, and now we're going to discussing some special bilinear forms and to explore their canonical forms, from which we can have better understanding of how these bilinear functions affect the structure of our vector space. Okay, so we deal with symmetric bilinear form and alternating bilinear forms. Okay, so this is just a pre-theorem, or let's call it a proposition. Okay. So F be any field and V is a finite dimensional face of that field. And if the characteristic of this field is not true, now phi is a bilinear form of V, then for any symmetric bilinear form, it has a matrix representation which is put into a diagonal one. Okay, and secondly, we consider those alternating bilinear forms, okay, without adding assumptions on the characteristic of fields. And this implies that, okay, there exists a matrix representation of phi as the following block diagonal form. See, the 2 by 2 diagonal block is given by 0, 1, 1 minus 1, 0, 1. And the order 1 diagonal part are given by 0. Okay. So these are the basic information that we can extract from either symmetric bilinear forms or alternating ones. Okay. Let's give a quick proof of this proposition based on our lemmas. So, if our bilinear form is just 0, then these two statements are clear, right? This is true. Okay. So now let's assume that phi is not always 0. Okay. Now, in the case 1, if phi is not 0, I claim that there exists a vector in alpha, say alpha in V, such that phi alpha is not 0. Why? Otherwise, phi vanishes on all pairs alpha, which just means that phi is alternating. But an alternating and symmetric bilinear form of a field with characteristic different from 2 must be 0. So such holds. Okay, it probably holds. This just means that we can take alpha to be the first basis vector in our set of bases. So in that phi can be write as say with the base B and starting from alpha equals say non-zero and this form, right? It can be congruent to such a form. And now, we would like to do induction on the dimension of V. So we need to write the whole space into a direct sum form. So the only thing is to check that this one-dimensional subspace, okay, yeah, if we want to achieve this, we need to check the one-dimensional space when our bilinear form restricted to it, which is non-degenerate. But this is clear from our assumption. So we already have this form, right? And now we just focus on this, which is called alpha and is called alpha, right? And by our inductive hypothesis, this diagonal form is clear. Okay. Now, for the second case, if this bilinear form is alternating and non-zero, then of course there exists a pair, say alpha beta, in V such that phi alpha beta is non-zero. And by rescaling, we may assume that this value is just 1. Right. Okay. So, but we already know that, okay, say for example, when we restrict to this two-dimensional subspace spanned by alpha and beta, okay, right, they must be linearly independent since phi is alternating. So then we will have the representation of phi of this form 0, 1, minus 1, 0. Right? Yeah. And again, when restricted to this subspace, our phi is non-degenerate, since the determinant of this matrix is non-zero. Then we will extend the basis alpha beta to an orthogonal basis of this whole space V. Alpha, beta, blah, blah, blah. And by our lemma, imply that, okay, we will have a block diagonal here, and 0 here, and stop. And again, we do induction. Hopefully clear. Okay. So basically, every symmetrical form over a field with characteristic different from Q, you can imagine it as a diagonal one. And on the other hand, for an alternating one, you can write it as this form, yeah, without loss of any generality. So my question is, do you have any counterexamples about this canonical form of a symmetrical one when the characteristic of field is 2? Yeah.
So let us take F to be the field of two elements, 0 and 1, and phi to be the form 0, 1, 1, 0.
Yeah.
Then phi cannot be put into a diagonal form.
Yeah, that's a nice observation. So you just mean that if you take F to be a special field, just consisting of two elements, 0 and 1. And in particular, in this field, we will have 1 equal to minus 1. Okay. And we will just construct a matrix representation of phi to be 0, 1, 1, 0, 0. So in this case, it should really check that it cannot be congruent to a diagonal form over this field F. Since this F only contains two elements, it doesn't provide enough elements to do this congruence. But so, based on this observation and the previous discussions, remark that, okay, you can view the second statement as a canonical form of an alternating bilinear function, but the second one is, cannot be called a canonical form since the diagonal element is not determined yet. But now, over some special fields, this situation can be solved. I will write this observation as corollaries. So, if we are lucky enough, our F is algebraically closed. For example, we take F to be the field of complex numbers, then it appears that every non-zero element, of course including 0, in C can be written as a square of another element. So, here we can put all the diagonal entries to be 1. Yeah. Let's say there exists a matrix representation of phi as diagonal either 1 if it's non-zero and 0. And there are in total R1s on the diagonal. And similarly, if you take our field to be the field of real numbers, then if there is a representation of phi as diagonal form, and there are several ones here, say R1 ones, and say r plus ones and some minus one here, say r minus ones and some zeros. Yeah. Since any element in R can be written as a sign multiplying a square. Okay. Now the important remark is the following. In the canonical form 1, when our f is taken to be an algebraically closed field, this numerical information R is uniquely determined by our bilinear form, and not depending on its which base you are considering, since it's just the rank of matrix representation, and the congruence equivalence doesn't change the rank. And there is a slightly non-trivial fact here. In this case 2, those r plus, r minus are also determined by phi. This is non-trivial. So if we could prove that r plus is determined, then of course r minus is also determined, since the sum is just r and I is determined. So the only thing is to check that r plus has some invariant explanation which doesn't depend on the choice of basis. Okay. So I will give you a direct explanation here. Say r plus actually equals the maximum of dimension w, where w is a subspace of V, and our bilinear form restricted to w is positive definite, which means that for any pair, for any non-zero pair, say alpha alpha, we have phi alpha alpha is strictly greater than 0. So so if we could prove this equality, then actually the r plus is totally determined by phi. Why does it hold? So for example, there exists a matrix representation, means that there exists a basis. And say, for example, we write the basis to be B, consisting with phi alpha 1, alpha k, blah blah blah, and alpha r1, say, r plus here. This corresponds to the first r plus coordinate. And if we take, say, we first prove that r plus is smaller than the max. It takes W would be the linear subspace spanned by this R1, alpha 1, R1, R plus. Then, of course, according to its canonical form, phi restricted to this subspace is positive definite, which means that R plus is smaller than the max. Okay. And conversely, if we just take the complementary of this of the preceding subspace W, say U to be alpha plus 1 to alpha n, then it is clear that phi restricted to this subspace is semi-negative definite according to its canonical form. Yeah, since the diagonal part are just a minus 1 and 0 here. So it means that any W from above with, say, phi restricted to W is positive definite, we must have the trivial intersection of W with U, right? Then, since U has dimension n minus r plus, such W must have dimension not exceeding r plus, which means that the maximum is always not exceeding r plus. So this finishes our proof. Okay. So I guess I made it clear, and I would like to leave you one exercise about these invariants of R plus and R minus. So actually here, R plus is called the positive inertial index of phi. And R minus is just called the negative inertial index. And our statement is just that, okay, up to the congruence, the positive or negative indexes will not be changing. But now, I will like to give you another stronger statement. Proposition. Okay. You can, so maybe exercise. You may imagine this phi to be n by n real matrix. Say A is this matrix representation under any suitable basis. In my matrix with coefficient in the field of real numbers, and instead of pick invertible matrix, we pick any matrix P in my matrix. Yeah, not necessarily invertible. Okay. Then we also consider the congruence by P. Say P transpose times A times P. This is also a symmetric if A is magic. Okay. Then we can talk about their inertial indexes, say R plus, R minus for A, and R plus prime, R minus prime for P for the congruence of A. Okay. And the conclusion is that no matter when P is invertible or not invertible, we always have these inertial indexes will not exceed the original ones. So this will be a non-trivial observation. And I want to mention here, also at the end of your linear course, that I believe that this exercise cannot be solved if you are only familiar with the matrix theory. You must know this characterization of positive inertial index. And actually this comes from the theory of linear maps, but not just playing the tricks of matrix. So this is the lesson I want to give you by this exercise. Thank you for listening.